All right, folks, let's talk about Bronsted-Lowry acid-base reactions. Now, Bronsted-Lowry acid-base reactions are not difficult. There's a couple tricks to them that I'm going to show you they're going to make your life a lot easier. So recall that Arrhenius theory was one theory for acid and base explanation to kind of explain in theory what was happening empirically with acids and bases. And we saw that Arrhenius theory is not that good. It's not terribly useful. Instead, we modified Arrhenius theory. And so when we modified Arrhenius theory, we took Arrhenius theory, which is acids are H givers and bases are OH, or hydroxide givers. We took that concept and modified it and said that when an acid reacts with water, it forms a hydronium ion, H3O+. And then we said when a base reacts with water, it forms a hydroxide ion, or an OH- ion. And that was an improvement on Arrhenius theory. But that's still a little bit more complicated, and actually there's a simpler way of explaining how acids and bases work. And that's what we call Bronsted-Lowry. I'm just going to say BL. Bronsted-Lowry acids and bases, super simple. In a BL acid, it's an H plus giver awayer. It's a donor, a hydrogen donor. And a Bronsted-Lowry base is an H plus taker. And so instead of having to keep track of two things, H's and OH's, the cool thing about Bronsted-Lowry is we only have to keep track of like one thing, and that is hydrogen ions, which we call H pluses, or protons. So you'll see to the right here I have a little snip of the acid-base table that you guys get in your data booklet. And recall, I've uploaded the data booklet, and there's also, I believe, an acid-base table inside of your textbook as well. I like this one. I think that this is a much cleaner and better laid out table. But a tour of the table first. Up here, we have the names of all of the different chemicals that we're talking about. We have the formulas of their acids, and then we have what are called the formulas of their conjugate bases. If you look at any of the acids and compare it to the conjugate base, so if I look at HCl and Cl-, the only difference between those two chemicals is that one of them has an H and the other one has lost its H. And that means its charge has gone down by 1. So HCl has a charge of 0, Cl- obviously has a charge of -1. So how do we work this chart? How do we use the table? It's really easy. Seriously, you guys are going to laugh at how sensible it is. If you took Science 20, this might look a little bit familiar to you. It might kind of look like the electrochemistry table where we talk about electron donors and electron acceptors. We talked about how electrons can go from one metal to another, and that flow of electrons we can use to power stuff. That's how batteries work. But anyways, let's see if we can do a couple of these reactions. And this is something that you absolutely need to know how to do. So let's get my little highlighter out here. I'm going to make it not opaque so we can kind of see the words. I want to do a reaction between HCl, let's make that bigger, between HCl and NO2, right there. So I'm reacting between HCl and NO2. And if you notice on the left side of the table, it says increasing strength of acid. That means that as you go up on the left side, the acid is stronger. Another way of saying stronger is that it gives away its little H plus much more vigorously. That's what strength means. So it's better at giving away its H. So if we look at HCl, it's at the top of the heap. This is the king in HC or in H giver awayers. It's the best proton donor. And we can see all the way down here, as the arrow goes down, it says increasing strength of base. That means that OH minus is the undisputed king and champion of taking H's. But since we're not doing a reaction with OH right now, we'll just do the reaction that we originally planned. So I have HCl, which I've written down, and I have NO2 minus aqueous, which I've written down. Now, the easiest way to read this chart is to go from left to right. And if you're going downhill as you go from left to right, that means that this reaction is very vigorous and it's going to happen with 100% completion. That means that the HCl, every single molecule of HCl is going to donate its H plus to the NO2s. So how does that work? Well, remember what we said earlier about the acid and base on the table. So the difference between an acid and its conjugate base is quite simply the conjugate base is missing its hydrogen. What that means to us is that HCl is our acid and Cl minus aqueous is our conjugate base. In other words, HCl gave away its hydrogen ion, its proton, and when it gave it away, what did it turn into but Cl minus? That's what's left. And the next thing to think about is, okay, where did that hydrogen go? Well, also quite simply, here's our NO2 minus. When it picks up a hydrogen, it becomes HNO2. And that is also going to be aqueous. And so NO2 was our base, so I'm going to mark it with the B, and after it takes the H from HCl, it is now our conjugate acid. So the idea here is that the NO2 minus ion gained an H plus and the HCl lost an H plus to become the conjugate base. Pretty simple. Makes a lot of sense. The table's quite easy to read once you get the hang of it. But the cool thing is, again, all you need to do is track one thing. It's where the H's are, where they're going. That's literally it. So let's do another couple examples really quick here. Let's take a look at H3PO4. That's phosphoric acid, and I'll highlight it here for us. H3PO4. Ooh, whoops. Got to turn the opacity down. H3PO4, boom. And HCO3 minus, boom. So remember, acids give away H's and bases take H's. So H3PO4 is going to be my acid, and that means that HCO3 minus It's going to be my base. I look at this reaction, downhill. That means that it's going to be going with 100% completion. We'll see something in a second that is not 100% completion. But for now, let's stick with those hundreds. We're going to do downhill. So, what does H3PO4 turn into when it drops an H? Well, it's really simple. You reduce the number of H's on the molecule by 1, and you reduce the charge by 1. But you could just as easily read the chart. So when H3PO4 drops a hydrogen, it becomes H2PO4 with a minus charge. And then what happens to HCO3 when it picks up a hydrogen? Well, its number of hydrogens goes up by 1, and its charge goes up by 1. So it was negative before, now it has a charge of neutral. And it used to be HCO3, but now it's picked up a hydrogen, so it's H2CO3. Last thing we need to do is label our conjugates. So my acid turns into conjugate base, and my base turns into conjugate acid. And there we go. There's another Bronsted-Lowry acid-base reaction completely taken care of. So 2 more examples here. I wanted to do some reactions with water, because you're going to see reactions with water a lot. So here we have H2SO4 and we have H2O, water. Now H2SO4 is one of these top 3 acids on your table. These are called strong. And that means that all of these, if they're reacted with water, will 100% react. Kind of like what we've been doing with the last 2 examples, and we had 100% there. This is going to follow the same pattern. So let's do our little arrow. So in this situation, H2SO4 is my acid, and H2O is my base. I know it's weird to consider water a base, but in this particular instance, yeah, it's a base. It's going to be accepting a hydrogen. So we'll do that reaction. H2SO4, when it reacts, becomes HSO4 minus. And that's aqueous. And H2O, when it is protonated, in other words, when it gets an H+, it becomes H3O+. That's our good old friend, the hydronium ion. Then all we have to do is label what's the conjugate of each. So H2SO4 was our acid, which means that HSO4 is our conjugate base. H2O is our base, which means H3O+ is our conjugate acid. So this is one of those reactions, again, that goes to 100% completion. So I'm going to label this strong acid with water. Last one we want to talk about is a weak acid with water. So I'll erase on my chart and we'll do the same thing, but this time we're not going to use one of the big 3. We're going to be using something a little bit further down. So hydrofluoric acid. Hydrofluoric acid, nasty stuff. Even though it is not a strong acid, it is still very dangerous. So we are reacting HF aqueous with H2O liquid. As we go from left to right, we're going up. In math, we'd call that a positive slope. In other words, I like to say it's an uphill battle. And whenever you have an up arrow like that, instead of a single-headed arrow on our reaction, we're actually going to do a double-headed arrow, and I'm going to say lesser than 100%. If you're a Chem 30 student, you're probably going to be looking at me funny or like making a face. Yes, there is a way to know what percent is actually reacting, but in Science 30, we're just going to say less than 100, and that's good enough for us. But what's going to get formed? Well, we do the same move that we did before. So HF is going to become F minus, in other words, fluoride ions just floating around in the solution. And H2O is going to become H3O plus. That's our hydronium ion. Just remember, since this does not go 100% of the way, and since HF is not a strong acid, we would classify this as a weak acid reacting with water. What that means is that not all of the HFs are dropping their hydrogens. So say we had, I don't know, 10 molecules of HF and 10 molecules of water. Less than 10 of the HFs are going to donate their protons to the water. It might be like 3 or 4. So that means that even after you mix these two chemicals together, you still have some HF and you still have some water that haven't done the reaction. Contrast that with H2SO4, sulfuric acid, strong acid, reacting with water. When you mix H2SO4 with water, if you have 10 molecules of H2SO4 and 10 molecules of water, when you mix them together, you get 10 molecules of HSO4 and 10 molecules of H3O. It reacts all the way, 100%. So in a nutshell, that is a Bronsted-Lowry acid-base reaction. I'm going to be uploading another video shortly about indicators, and I'll be uploading another quick video about how to calculate pH and H3O concentration. That'll be up a little bit later today. Thanks, guys.